In this video, we solve problem number 4 from Differential Equations, quiz number 5 from the spring 2021 semester. This problem covers variation of parameters. Now, there were multiple forms of this quiz, so not all students saw this problem. Okay, here's the problem statement. It says, the following set of functions includes two known linearly independent solutions of the associated homogeneous differential equation on the interval from 0 to infinity. It says, use the fundamental set of solutions above to find the general solution of the DE using variation of parameters. So we know that these are solutions to the corresponding homogeneous problem. So that means, since this is a second order differential equation, that y sub c is equal to c1y1 plus c2y2, where y1 is this first function, and y2 is the second function. And now, rather than solving the homogeneous problem, we're going to use these two functions to solve the corresponding non-homogeneous problem right here using variation of parameters. So I've got a differential equation. It does not have constant coefficients. So when I find y sub p, I need to use variation of parameters. Since this is second order, y sub p will be equal to u1 y1 plus u2 y2, where u1 and u2 are non-constant functions. So u1 is a function of x. It's not equal to a constant. And u2 is also a function of x, not equal to a constant. Well, then we're going to skip some steps. It's the only method where we skip any steps. Then, by variation of parameters, if we substitute into the differential equation, we differentiate twice, we substitute into the equation, we simplify. Eventually, we have one equation with two unknowns. And then we turn that into two equations and two unknowns. And then the solution of that system of two equations and two unknowns leads to the following formulas for u1 prime and u2 prime. u1 prime is equal to w1 over w, and u2 prime is equal to w2 over w, where w is the Wronskian of those two functions, y1 and y2. And w1 looks just like that, but we replace the second, or the first column with 0 and f of x, and we leave the second column alone. And w2 looks like the Wronskian, but we replace the second column this time with 0 and f of x. Now, f of x is related to that function on the right-hand side of the equation. But be careful, it's not this function. F of x is the function that we have over here when y double prime has a coefficient of 1. So you have to divide the entire equation by x squared. And that's going to lead to, well, x to the 3/2 divided by x squared is x to the 3/2 minus 2, or 3/2 minus 4/2, which is negative 1/2. This is our f of x when the coefficient of y double prime is 1. That gives us our f of x. Okay. So we have stated the formulas for u sub 1 prime and u sub 2 prime. Now we just need to compute the w's and then substitute. So w is this. It has x to the negative 1/2 cosine of x there, and then its derivative down here, and x to the negative 1/2 sine of x over here, and its derivative below that. I'm just going to do a little bit of scratch work. Do this in blue. When I take the derivative of this, I need to use the product rule. So I'll think of this as my first function, and this is my second function. We'll have, according to the product rule, derivative of the first, which is negative 1/2 x to the negative 3/2, because you're bringing your power down, multiplying by x to the 1 less power. It's derivative of the first times the second, plus the derivative of the second. Derivative of cosine of x is negative sine of x. And we're multiplying by the first function, undifferentiated, which is x to the negative 1/2. And you can factor out a negative 1 if you want to, or you can factor out a negative 1/2 x if you want to, or x to the negative 1/2 if you want to, sorry. I'll factor out the negative and the x to the negative 1/2. So this is going to be this times a positive 1/2 times an x to the negative 1, because this times this would give me x to the negative 1 minus 1/2, which is negative 3/2, times cosine of x. And I factored out this negative and this, so we're just left with a sine of x on that second term. A lot, that's what goes right here. And then over here, we're going to have the x to the negative 1/2 sine of x and its derivative below that. And if you wanted, you could have just left that alone. I chose to factor, hoping that something would simplify. We'll see if it does. I'm going to use the product rule again. We have the derivative of the first times the second, undifferentiated, plus the derivative of the second, which is cosine of x, times the first, undifferentiated. If you want, you can factor out the x to the negative 1/2. You don't have to, though. So we have a negative 1/2 times x to the negative 1 times sine of x, because that times that would give us that, and then this times a positive cosine would give us that second term. Wow, that Wronskian's got a lot going on, but hopefully there will be some simplifications. Okay. Remember how this works. We multiply across this diagonal, multiply across that diagonal, and subtract. The Wronskian is this times this. X to the negative 1/2 times x to the negative 1/2. Add the exponents. It's going to be x to the negative 1 times the cosine of x. Times all of this. Now in hindsight, I'm thinking it may have been better to not factor. That's okay. We'll distribute in a minute. And we're subtracting a negative, so we're going to add this times this. X to the negative 1/2 times x to the negative 1/2 is x to the negative 1 times sine of x times all of this. And distribute now, hoping that we'll have some cancellations. Negative 1/2 comes down. X to the negative 1 times x to the negative 1 is x to the negative 2. I've got a sine of x times a cosine of x. Then I've got a x to the negative 1, or I'll call it 1 over x. And cosine times cosine is cosine squared. Here, I have a positive 1/2. X to the negative 1, x to the negative 1 is x to the negative 2 times sine of x times cosine of x. And then this times this is going to give me this, which I'll call 1 over x, and sine times sine is sine squared. And even though it looks messy, what do you know? This term and this term are identical, but with opposite signs, and so they're gone. And then these guys have a 1 over x in common, so I can factor out a 1 over x from here and here. And I have 1 over x times cosine squared is my first term, and 1 over x times sine squared is my second term. And that's 1. So the Wronskian is just 1 over x. Very nice. It looked really bad, and the differentiation was a little tricky, but we got to this beautiful simple function. All right, so that is our W, and W1 looks just like W, but we replace the first column with 0 and f of x. And remember, f of x was this x to the negative 1/2. So we have 0, x to the negative 1/2, and over here we have x to the negative 1/2 times sine of x. And then all of this stuff about we're going to multiply it by 0. So I'll write it in just for completeness. But I know it's going to cancel. That's going to be nice. So we'll have 0 minus this times this. So it'll be negative. This times this is going to give me an x to the negative 1 times sine of x. Or if you prefer, you can call that a negative 1 over x times sine of x. And that's going to be nice because it's going to cancel with that. And then we're just going to have a sign. Very nice. Okay, W2 looks very similar, but you leave the first column alone. And you replace the second column with 0 and f of x. So our first column was this. And our second column is 0 and x to the negative 1/2. When we multiply across this diagonal, we get this times this is going to be an x to the negative 1, which is 1 over x times cosine of x. And then we're subtracting something that is 0, so we're subtracting nothing, which is just the same as doing that. So we have our w, which took a little bit of differentiation and simplification, but it's simplified really nicely. And we computed our W1. And we computed our W2. And now that we've got the W's, we can substitute those into these formulas to find our U1 prime and U2 prime, and then anti-differentiate to get U1 and U2. So we had U1 prime is W1 over W. Let's see. W1 was negative 1 over x times sine of x, and we're dividing by 1 over x. Well, that's easy enough. These guys reduce. We just get sine or negative sine of x. And so U1 is the antiderivative of negative sine of x. So I believe that's cosine of x plus a constant. We're going to choose that constant of integration to be 0. If you're ever unsure about your SIGN sign with your trig functions, remember the derivative of sine is positive cosine. So when I take this antiderivative of cosine, derivatives of cofunctions are always negative. Derivative of cosine is negative sine. I always check by differentiating, so I know I did it right. Okay, so that's U1 prime, and U2 prime is similar, but we use the W2. W is still 1 over x. W2 is 1 over x times cosine of x. So you substitute that in. And we just get cosine. Easy breezy. So U2 is the antiderivative of cosine, which is sine. Of course, you need an angle, x plus c. And we don't want to multiply this c by a y2. We don't want a constant times y2 as part of our y sub p. So we'll choose c2 equals 0 there. All right. So now we've got our U1 and U2. So y sub p is U1y1 plus U2y2. So we're going to substitute our U1, U2, of course y1 and y2, into the form of y sub p and simplify. So U1 is cosine of x, and y1, remember at the very beginning, we chose for this to be our y1, and we chose for this to be our y2. So y1 is x to the negative 1/2 times cosine of x. Negative shouldn't be there. X to the negative 1/2 times cosine of x. And u2 was sine of x. And y2 was this, x to the negative 1/2 times sine of x. And of course, we've got a cosine times a cosine. So that's cosine squared. And we've got a sine times a sine. So that's a sine squared. Do you see it coming? These guys both have an x to the negative 1/2 in common, so we can factor it out. We say x to the negative 1/2 times cosine squared would give us the first term, and x to the negative 1/2 times, that's sine squared, would give us the second term, and sine squared plus cosine squared is 1 if the angles are the same. So we have x to the negative 1/2 as our y sub p, which is very nice. So our general solution, and we were asked to find the general solution, is y equals y sub c plus y sub p. And y sub c is just c1 y1 plus c2 y2. And y sub p turned out to be x to the negative 1/2. And these are all well defined as long as x is positive but not 0. So once you find your y sub p, your general solution is y equals y sub c plus y sub p. And we always like to state our interval of existence.